This is the first in 6 videos on basic DC motors and sufficient discussion for laboratory study of a basic permanent magnet DC motor. On this slide here, in a few slides to follow here, I'm going to talk about DC motor types and how we classify them. They're extensively used, can be low cost. A little picture here of very cheap little motors that you can find, for example, online, like on places like Amazon. These are about $10 for 10 motors, so these are very low cost. But the nice thing about these motors is if you look inside here, you can see the brushes and where the brushes are here that are spring loaded for this is the commutator, and here are the brushes, right? And these contact here to so that, you know, you can imagine here's where you put in some voltages. A DC voltage input here sets up the current that goes onto the rotor. This little picture here from a textbook shows that construction. So you've got to get current right onto that rotor, which is spinning. Permanent magnet DC motors have a field here that's set up by permanent magnets on what's called the stator, which is on this side, the outside. The rotor part and that circuit constitute what's called the armature. Again, here's the commutator and then the brushes in this cutaway view of this DC motor. That field for DC motors can be constructed in a lot of different, can be configured in a lot of different ways, and sometimes you'll hear that's a shunt DC motor, and you can see that relative to, and this circuit schematic here represents that electromechanical conversion that's occurring in the motor, right? That can be either a motor in action or a generator in action. In this case, you put in input voltage here. The field is excited in shunt with the actual the shaft is here, that electromechanical conversion. So a shunt motor, or in parallel, a series DC motor has the field excited by the same power that's going through the actual electromechanical conversion. And you could also have a separately excited DC motor where you have a whole other power supply that's giving power to the field. Those stand in contrast, right, to the permanent magnet DC motors that I showed before, where the field itself is built up by again, a permanent magnet structure on the stator of the motor. So the nice thing about this is, whereas these guys, right, need to have power to create the field that the current on the rotor will interact with to generate torque, say, the permanent magnets here are separate source of energy that is going to interact with the current that you're pumping in via, right, the brushes and the commutator. So these can be a little bit more energy efficient. A lot of very small motors you see in anything from small toys all the way to windshield wipers and so on are of this construction. Slide here just summarizes the permanent magnet DC motor has, again, permanent magnet has a very simple construction and relatively easy to find these devices in a lot of systems where you need some form of electromechanical actuation. Eliminates the need for field excitation, as I just showed, making these motors efficient for a broad range of applications. Drawback is you have those brushes, right? And all of these motors have brushes, and there can be wear. They're not always very good in, for example, clean rooms and so on. So that's where you bring in brushless motors, where you don't have those commutators. Give you an idea, this is a little motor we use in the lab for this lab study. Very low cost motor. Currently buying this off of the SparkFun website for about $6. You can see in this little photo here, here's your permanent magnet, right? You know, north and south. What's happening, right, is the field is coming through here, and then the outer casing here closes that flux path on each side, right? Okay, so the flux is passing through there, and it's being contained within that structure. Okay, the rotor is shown here, right? The copper windings, and there's your commutator. So I'd like to take these apart. If you buy one of these, if you want to take it apart, make sure you buy an extra one, because these don't come back together very easily once you take them apart. We did this just for the illustration of this for this lab. This is a nice little package for this lab study. It's got a metal final gear, but most of the inner construction is actually plastic that forms up the gear head for this motor. I'll show you a photo of the constructed motor in a second. Attached onto the end of this shaft when it's constructed is a magnetic disc that interacts with this encoder. So you have both the motor actuator as well as the encoder, which is used to measure the motor speed. I'll be talking more about that in a subsequent video. Okay. So this shows the motor and gear head in construction. So you can see how the permanent magnet DC motor, it's got a pinion here that interacts with the crown gear, and then when that's all attached, all this structure here forms that the final gear, the gear head, right? So this is it gears down, very high speed rotation here, and finally very relatively low speed rotation. The top, if you go back to that subsequent slide, a previous slide, oops, sorry, too far. Here, the only specifications given for this by this manufacturer are that this motor runs anywhere between 3 and 9 volts. You shouldn't exceed 9 volts on this motor, burn it out. It says that there's a gear ratio of 1 to 48. It's gearing down, right? And then the high-speed motors, at the rated voltage of about 4.5 volts, it's turning at 90 RPM, okay, revolutions per minute. We actually deconstructed that gear head, counted the gears, and it turns out this is more of a 45 to 1 gear ratio. And you can see, how those gears were counted and so on, and how those calculations were done, if you have some time, to show that that's actually 45, and that actually jives with some of the measurements that we've made in the lab. I'll close this video now, and in the next video talk a little bit about how we assess performance. Here we have a spec sheet for this manufacturer, that doesn't give us a whole lot of information about how this motor might perform. So we're going to look at how we can build the model to assess performance.